Well, first of all, many thanks for the audience. So, in fact, this is a continuation of the strategy that our PDEC course has in order to have well, short seminars for the dissemination on this research that is being conducted by our PhD students. And this has mainly the aim that the students knows, in fact, what we are doing, and at the same time, they can stretch collaboration each other. And well, I start thanks to give my congratulations to Kamiar, because in fact, during the last months, he did an extraordinary job in order to develop a pre-processor and post-processing tool for FEMIX software. And well, in fact, he dedicated almost full time during these last months to this activity. And in fact, this is an activity whose results can be used by the other students. So it's in fact a very nice attitudes. So well, Kamiar, so the word is yours. So please go ahead, and again, many thanks for your effort that you are doing.
Thank you, Professor. Thank you for introduction. So I'm going to share my screen. Okay. Good afternoon. My name is Kamiar, and in this season, I'm going to talk about a new pre- and post-processing user-friendly application for Femix computer program. At first, I will talk about the finite element analysis, and then I will introduce the Femix software. And in the next step, I will talk about an integrated application, which is Femix Pre and Post. And finally, at the end of this season, I'm going to do a practical example by using this developed application. But what is finite element analysis? The finite element analysis is the simulation of any given physical phenomenon using a numerical techniques, which is called finite element method, which already we are familiar with this concept. Finite element is used by engineers for simulate physical phenomenon, which in our case is structural elements. For example, we have here in this figure, we have a beam. We have a reinforced concrete beam, which already tested by experimental tests in the lab. First, we discretize and extract the geometry of this beam. We have the dimensions of the beam, and also we have the material properties. And then we discretize this geometry to finite meshes. And after finite element analysis, we will have the output, which is could be, for example, the deformation, the stresses, strains, and also crack patterns, and some responses of these structural elements, such as load and deflection. Finite element analysis has different steps, such as pre-processing, discretization, solution, and post-processing. Here in these steps, the first step is model creation, and then we discretize the model to meshes, which is mesh generation step, and then we have attribute assignment, such as the supports, loads, material properties, and then we need a finite element solution, which here we will use Femix, and then we need to interpret the results for result visualizations. And these 5 steps could be done by an integrated software. There are a lot of softwares in the market, such as Abacus, ANSYS, Diana, and many other softwares, which already has that kind of integrated interface for doing those 5 steps. But the most disadvantage or problem of this software is that we need a license to be able to use them, and also they are so general, and they are not specifically for structural engineering, and it's more complicated to learn and use those softwares, and also we don't know exactly their background. But also for those steps which we need to do for doing a finite element analysis, there are some free tools for different steps. For example, we have Gmesh, which is a free mesh generation application. For mesh generation, Gmesh is an open source and free also 3D finite element mesh generator with a built-in CAD engine and post-processor. Gmesh has more than 500,000 of lines, and it means that it's very powerful. And it supports advanced meshing strategies. It has an interface, which we could use that interface for doing the model and using the interface for mesh generation. And it supports comments. In this image, we can see the interface of the application. This is the Gmesh interface. We could use geometry for creating the model, and also and then after creating the model, we could use mesh for mesh generation. And if we are more advanced user, we can use the Gmesh comments for creating the model, and also modifying the model just by changing the parameters. And also for visualization and post-processing, there are many softwares. One of them is Paraview, which is an open source and multi-platform data analysis and visualization application. Paraview, I will show you here the interface of Paraview. Paraview has a lot of capability for showing the different types of meshes. We have different types of contours. It supports also programming, and is a free software. And for processing, I'm going to introduce Femix, which is based on the finite element method and introduces a large library of types of finite elements, which is complemented with a set of points, lines, surfaces, a spring, and support different types of finite elements models. It supports static and dynamic analysis of structures. Also, different types of linear and nonlinear material and geometric behavior could be performed by Femix. Different types of elements supported by Femix, such as 3D beam, plane stress, plane strain, plate shell, and cable interface, embedded cable, and many others. Direct and iterative solvers could be done by Femix, and the founders of Femix are Professor Azevedo and Professor Barros. And also there are a lot of contributors which already made Femix a very powerful tools for analyzing any types of finite element problems. In this slide, we can see the different models which already done by Femix. It shows that very complex structures and very complex problems could be solved by Femix. For analyzing with Femix, we need to generate an input data file, and each input data file contains different blocks. For example, we can see 2 different blocks. Each block started with a keyword and ends with the same keywords. For example, here we have group names and ends with /group names. It means that the different groups are defined within these blocks. The lines started with sharp sign will be considered as comments. We have a counter in each block, and then we have a help, something to introduce the different parts of these blocks. And we have the number. For example, the first group is Femix group, and then we have the other groups. The same strategies will be used for defining the different types of input which we need to introduce for defining any types of problem, and then going to the next step. Femix generally has three main applications by itself. First one is pre-Femix, which it will check the model and will check if everything is fine. And then when we saw the success command, we can go to the next step, which is Femix. Femix will read the input file and will run the analysis. And after the analysis finished, we will go to post-Femix, which we could generate the output, which are in the format of text file, as the input file was in the format of text file. And it supports different types of outputs. By writing the help command, we will see the different types of output supported by post-Femix. And finally, there is a tool called Gmesh. We can interpret the output, such as here we can see the stresses on a beam. But what if we had an integrated application for having all of those steps in one single interface? An integrated application which uses Gmesh for model and mesh generation, uses Femix for solution, for FEM solution, and Paraview for model and result visualization. We had different steps, as I explained before: model creation, mesh generation, and attribute assignment. And then we can send them to FEM solution. And finally, result visualization, which are the main steps for solving any types of finite elements problems. Here, we worked on an integrated application which could interact with these different types, three different types of external application, which could be used. For example, we can do the model here, integrated application. We can send to Gmesh and then generate the mesh and get back the mesh, and then complete the input file for Femix, which is model generation, and then send it to Femix. And after finite element solution, after solving the problem, we can get the results and send them to Paraview for results visualization. Femix PrePost, which is the developed software, supports different types of elements, which already these elements are supported by Femix. But keep in mind that triangle and tetrahedron element, however, are supported by Femix, but these two elements have some limitations in terms of material, which doesn't support these two elements yet. But we can use, for example, for rebars, we can use line. For plane stress, we can use quadrilateral, and for 2D elements, hexahedron. It also supports the quadratic elements and also interface elements. However, I have not bring all of the supported interfaces here. The difference between interface and the line interface is that this is just, it has two nodes, but here we have 4 nodes, which are the intersection between interface and the mother element. But we need to be careful about mesh generation and using the mesh strategy for FEMIX application. It means that the mesh need to be coherent. For example, for embedded cable, we need to keep the nodes of any embedded cable within the mother element. It means that the node of the embedded cable should be on the edge of mother element, or it should be on the corner of each mother element. Also in line interfaces, for example, here we have a line interface, which could be a rebar, and this could be a plane stress. It needs to keep the nodes of any line element in the corner of the plane. This is a quadrilateral element. However, these two types of mesh strategies will be considered by new developed application. They will be generated automatically. This is the interface of new pre and post processing application for FEMIX program. It consists of different parts. This is the main window, which could be used for representing the results, viewing the model and different visualization. We have a left menu, which consists of different parts. I will explain each part in detail later. We have the property window for controlling the view to see the nodes, the labeling the nodes, and also we can hide or show different groups in the model. We have the top icons for controlling the model, which already exists in any application for creating a new model, opening an existing model, and save the model, and also running the FEMIX, and an icon for extracting the results. Also, we have a different section for controlling the view. We can change the view and many other options. At the bottom, we have the FEMIX input file, which already generated after changing its, for example, when we change a parameter, it will apply to this section, and we can check the changes in real time. And also, if we change in this data file, it will apply in the model. And we also have a comment section, which could be used when we are working on the model and mesh. In the left tab, we have different parts. The first part is the model, which could be used for modeling any types of point, line, shell, or 2D elements and 3D elements. We have different options for controlling and drawing the model. We have point, line, and many other options, which is almost enough for any type of structural element. However, if we have a very maybe complex model, we can use Gmesh and then import the data into the application. The next part is the mesh. For example, here first we model the geometry of our problem, and then we go to mesh and we choose that model and then generate the mesh. We have different options. It supports a structure or unstructured mesh. It could be different types of mesh, which we already talked before. We could just check this item for having the quadratic mesh. We can control the mesh size and minimum and maximum mesh size. And at the bottom of this panel, we have two options. And the first one is for generating the interface elements. By checking this, the nodes will be kept duplicated, and then the interface element will be generated based on the mesh strategies, which was having the mesh in a coherent way. And finally, we have an item for generating the embedded elements automatically. In this way, if we check this item, the application will not use these parameters and will generate the mesh based on the intersection of the rebar and their mother elements. After generating the mesh, by clicking this, we will generate the mesh. After generating the mesh, we will see the generated mesh, and if it's confirmed, we can add these mesh to FEMIX application, to FEMIX input data file actually. Then after generating the mesh, we will go to FEMIX tab. In FEMIX tab, we have different parts. At the top, we can see all supported keywords by these applications. In this tree view, all assigned keywords which already defined before in the input file will be listed. And for example, here we have a group names which contains 8 group, and so on. Like the other parts, we have different keywords and the number of items on that section. Also, we have a shortcut for the items which we use the most. For example, the main parameters, supports, material, and other options which we usually use the most. And after running the analysis, we can go to result. In result, we have the displacement, stress, strain, and different types of available results. Then after selecting the desired result, we can select the sub results. For example, here we have the displacement in Z direction is D3, and then we choose the S step. This is S step 55, and we have some options. We can see the deformed, undeformed, or both deformed and undeformed shape on one single window. We have other options such as the scale factor and others. And then we will see the results on the result window, the main window. Also, if we want to draw some graphs, we can use the graph tab. For example, here it's on for drawing the load deflection, displacement, and reaction forces. We can apply different multiplier to the values for controlling the output. And then here we can just write or select the list of the nodes, and by click on plot the graph, we will have the generated graph. Okay, for practical example, I have chosen an example from this paper assessing the applicability of the Smith crack approach for simulating the behavior of concrete beams, flexurally reinforced with GFRP bars and failing in shear by Professor Barros and others. In this paper, we have a concrete beam, reinforced concrete beam. I want to select one of these sections because it contains different sections. At first step, we need to extract the geometry of the beam. For example, I want to consider the left support as the center of the coordinates. It will be my 0, 0. We need to, the axes are important. We need to have Y, Z for the axis. I highlighted the most important dimensions and properties. In this beam, the height of the flange is 340, and for web is 60, and the width is 150, and 400 for the flange. And also we have 3 rebar on the bottom, which are GFRP bars. And also the load is located on 1100 from the left support, and the other dimensions which are available on this shape. Okay, I'm going to FEMIX application, to pre-post FEMIX application. Okay. This is the main window of FEMIX PrePost. I want to create a new file. I just click on new. I choose a name. For example, it's a beam. First, I'm going to model. I noted the old coordinates for drawing the model, because we need to extract the coordinates of each corner in order to draw the shape. This is my first model, so I click on new part. I name it as web. Okay. The web is a 2D element. First, I define the points. Here, when I click on point here on the bottom, I see it says that it's a new point. Enter the point coordinates. So the coordinates of first point is 0 and minus 200 and 0. The second point is 0 and 2000 and 0. I want to click on zoom fit to see the changes. The third one is 0 and 2000 and 340. In case we made a mistake, for example, the last one is 0 and minus 200 and 340. But for example, I want to choose a wrong parameter. I entered this coordinate by mistake, so I can click on delete selected item and click on this point, and here we can see that in the bottom it says that, are you sure you want to delete this point? So I click on yes, and it will be deleted. Also, we have one option for editing these points. I click on this. The coordinates of the point will be visible in this notepad file. I can just copy and enter the coordinates in this file. Instead of entering the application, I want to enter the coordinate of last point. It's 0 minus 200 and 340. Yes, and I just refresh the point, and I will have the 4 points. The next step for shell element is drawing the surface. So I click on surface. I can just click on different points, and we will have the surface. We have different ways for drawing the surface. For example, here when I click on surface, I just, instead of clicking on the interface, I can just could enter the name of the point, and by clicking on enter, it will be considered as one edge. The next part for our case is the flange. I name it as flange. This is 2D element. Same as before, I have to enter the coordinates of the flange. 0 minus 200 and 340. 0, 2000. 340, 2400, 0 minus 200 and 400. So I have all points. I click on surface, and here, instead of clicking on the point, I just enter the name of the point. It's 0 to 1 to 2 to 3. We have the flange of our beam. The next part is could be the bar on the top. The bar on the top is a 1D element. It could be wire or cable, or it's a 1D element. First we need to draw the point 0 minus 200 and 395, and then the end 0, 2000 and 385, and then we draw the line. It's 0 to 1. And next one is bar on the bottom. It's 1D element. Like the other one, it's 0 minus 224 to 0, 2024. And I draw the line from 0 to 1. And also we have stirrups. They are wire elements. I draw the coordinates. It's 0 minus 20 and 0. It's 0 minus 20 and 400. And also I can just click on edit on Notepad and just input from, if we have another model, we can just copy from from an existing model. I had these in another model. I modeled it before. I just open the file. It's a stirrup. Edit. Stirrup. We find an existing model. Image 2.
Kamiar, we are not seeing what you are doing now.
You don't see, okay, I'm looking for an existing file to just copy the coordinates instead of entering coordinate. I can just easily
Okay.
I couldn't find it. Okay, let me just enter it fast.
Hey, take your time.
Okay,
so
I couldn't find it. No problem. We can just easily copy from another file and just copy the coordinates here, and it will be easier to complete the model. The next point is 0 and minus.
What does it mean is that we can have a library of, for instance, reinforcements predefined, and then we can immediately
copy and paste the coordinates.
Yes,
exactly. If we want to generate the different models and with the same geometry, we can just have the coordinates and just copy and paste the coordinates. We don't need to enter the coordinates each time because they are editable. And 0 and minus 170 and 400. The next one is 0 and 1 to 40 and 0 and 0. 40 and 400. 0.
So you see, Kamiar is introducing the extremities of the bars that is simulating the stirrup. So it's a linear element. So he's indicating the coordinates of this the extreme node also, because it's a bar element of 2 nodes.
Yes. And the last one is 0, 1840 and 0 and 0, 1840 and 400. I entered one coordinate, I think it's wrong. This one. I just go and edit the coordinate and close and save and then refresh it. After refreshing, we will have the old coordinates. And just I can click on the line and use the interface for drawing the different stirrups. 7. I didn't introduce this. I will introduce later. It's after 0.8. It was 400. I just copied from another point and paste here and just change the coordinate of the Z. And this is the coordinates. Okay, I'm checking the model. Okay, it's fine. And the next one is the Z bar. I just named the Z. For Z bar, I want to copy. Here we have an option for duplicating any model, any part. I duplicate it, or I will rename it to a stirrup, for example, Z. And then we have something like this for the Z bar, and then we can remove the unused parts. And you can see that after deleting each point, the number of points will be regenerated. You don't need this. Cancel. And we don't need these 2 points. Okay, now we have all parts of the model, which was the web, flange, the bars on the top and bottom, stirrups, and the Z rebar. The next step is going to the mesh. The mesh, first we want to generate the mesh for the web. Here we have the model of the mesh. We need to check the different options for the meshing. We can select different mesh strategies. For example, here I want to choose 30 for the mesh size. First, I want to generate the mesh as an unstructured mesh. I click on generate mesh. It will just show the mesh, which we can see that it's an unstructured mesh. So I change it to structured mesh and generate again. And now we can see that it's a structured mesh. So the dimension of the mesh is 30 millimeters. We can define the minimum and maximum element size, which here I put it as minimum maximum because I don't want to limit them. If we have a quadratic mesh, just I check quadratic mesh and click on generate mesh. And now we see that the quadratic mesh will be generated. Now I just uncheck the quadratic mesh. So if it's confirmed, I click on add to Femix. So the mesh is already added to Femix. Next one is the flange. I want to keep the previous options, generate the mesh. The mesh generated, I add it to Femix. Now it contains all web and flange. In the left and the right panel, we can see the different groups. The next one is the bar on top, but now I don't want to mesh by myself. I want to use another option. It says that automesh as an embedded element. If we check automesh as embedded element, it will be checked by its mother element because it's an embedded cable. So I will check automesh and then generate the mesh. Now we can see that it's the mesh has been done by the application. Now, because the mesh are structured, it's not that much feasible, but for stirrups and the Z bar, we will see what is the difference between meshing by automesh and meshing by Gmesh, which is defined by these parameters. So
Kamiara, I don't know if you generate the web and the flange, I suppose the web with the quadratic and
yes.
the flange with the quadrilateral. Maybe I don't know.
No, they were the same. I just
same. Okay.
Yes, they were the same. I just showed
this is
different
important.
types of meshing, but finally I did the same.
Yeah,
mesh.
It's important because we need to have continuity. Okay,
Yes,
good,
yes, of course. Now I will add mesh to Gmesh to Femix. Now we can see that the bars added to the model. If I click on node, we will see that the mesh in the web and the flange are in the same mesh element type. And then bar on the bottom, the same method, add to Femix. Now the bar on the bottom has been added. The next one is a stirrup. A stirrup, if we want to mesh the stirrups between by using the mesh option, we need to maybe discretize these stirrups in the web and in the flange and to keep the mesh coherent. But also I want in this model, I want to use the auto mesh. So I click on generate mesh. Now it takes time because it will check all of these parts with the mother element to find the intersection between each element, each line and the mother element. Now I will add it to Femix. And finally, we have the Z bar. I want to generate a mesh. And now we can see that the nodes, I just click on label the nodes. As you can see, the nodes are in a different location. They don't have the same lengths because the intersection between these embedded elements need to be coherent with the mother element. I added to Femix model. I just want to check the model. As you can see, for example, here, if we check the nodes are in the edge of their mother elements. So the mesh are coherent. So the model is finished. The next part is Femix. I'm going to Femix. In Femix, we have different options. We can just double click on this tree view or just click on this right control panel, or I can click on the top combo box to just, for example, the main parameters, to modify the main parameters. We need to choose a name, a title for the model. This is a material nonlinear problem. I want to use, for example, arc lengths. We need to choose a point number, and the degree of freedom is D3, and the displacement increment, for example, 0.5. I need to find the point number which the displacement will be applied. I will find it later. First, I need to introduce the different parts. For example, the supports. I want to check the coordinates of the node. I don't want to extract the exact coordinate. I just want to draw a model. For example, the point number 85, 11. I just note this point, and the right one must be here. '71, and the loads. I don't want to extract the exact coordinate. I just want to present the process. Okay, this is the point coordinate. I just copy it. I'm going back to the model. The coordinate of the point number, and displacement rate is here. Okay, now I'm going to support. We have two supports. We need to choose a group. Phase is 1, point number is 11, is the 3 because it's Z direction, and the next one, Femix group, phase 1, the point number is 171. I want to fix it in D2 and D3 direction. Okay, and the load, we can define the load here. We need to define a load case parameters, which I just name it as load 1. It's a Femix group. Default. After defining the load case, we can define, for example, here we have a point load. The point number is 105. 0, 0, minus 1, 0, 0, 0, and the load case is load case 1. Okay. Now, after refreshing the model, we will see that we defined a support here on the left and one support here on the right, and this is the point load, and we can control the viewing of the load. For example, load case of 1, it was load 1. If I uncheck, it will be disappear, and I can do the same task for example, in the support in bar and Z bars. We can control the visibility of different groups and different load and support conditions. And then for this model, we need to define a material. I'm going to define the material concrete and material nonlinear model 104. This image is not defined. I opened it in the wrong direction. The delay. Here we had the material concrete 104. We have the list of material. We can define the material in this table, or we can just right click on this panel and just click on add a new row. In this window, we can define the material properties, or if we already defined it before, we will have it in our library. Now I already defined this material. It's a nonlinear material. This is the material. I click on load, and the information will be loaded. Okay, now the material is already in our table. I can do the same procedure for defining the steel. I want to add an isotropic material for the steel, linear isotropic material. I add a new material. I already added the steel load. Okay, and I want to already add a new material. It's GFRP linear load. Okay, okay. Now I define the material, I define the support and load conditions. Now I can go to element properties and modify the model. I double click on element properties. These groups already imported from the mesh part. When we import some model, they will be automatically in this table.
Amir, I suppose you have not yet defined the thickness. Are you planning
No,
to
I know. I want to do it here because it's easier. Sometimes it's instead of going to different parts and define it separately, it's easier just come to edit the row. For example, here we had the web. It's a plain stress squad. Material type is 104. I already defined this material. I can just choose it. But for geometry type, it's laminate thickness, but I didn't define it. There is nothing in this table. So I can just click on add a new item. I can do it here. Add a new row. And the name is, for example, web. The thickness is 150. Okay. And now it will be added to this box. I can choose it. And also for integration, the integration type is Ghost Legend. And the integration, there is no integration here. I can just click on add a new item. I can define the integration by these keywords directly in this table, or it's easier to add a new row and just click on, I want to use the auto generation. I just click on plane stress quad and generate numerical integration. We will see and we can check the generated numerical integration and then click on OK. We will have the integration type. Let me add the embedded cable too. We had the embedded cable 2D and generate. OK. So I already defined two types of integration. OK. Now here we have a plane stress. I just click on plane stress. OK. We need to do the same procedure for all types of material and the groups which already exist here. But it will be faster when we define one. We can use some properties in the next items. This is plane stress, material is 104, but the thickness is different. I didn't define it here. I can just define in the table. The flange is 400, and I already defined integration in the previous step. Okay, and the bar in the top, I want to use linear isotropic material. It's steel, the geometry type. When we use this table, the items will be limited, so it will be easier to just choose between supported elements. For example, here, the embedded cable supports the cross-section areas. Just we need to define the cross-section areas. There is no cross-section areas. I just click on the cross-section table. I need to define the area of each bar. I already noted here. The bottom bar is 3T18. So the cross-section area is 763. The next one, top, is 2T10. The cross-section area is 157. The stirrup is 100 because we had 2 legs. It's 2, 8, it will be 100, and the Z bar is 154. Well, now this is a top bar, and this integration is embedded cable, which I already defined before. Now I have it, and the next row is embedded cable 2D. Material type is isotropic steel. It's GFRP. It's bar bottom and embedded cable. Embedded cable 2D. You can just click on the item and just choose a stirrup and embedded cable 2D. And the last one is embedded cable 2D, linear steel, cross-section area. This is the Z bar and embedded cable 2D. And in this table, we can check our input. Now I can see that this is wrong. I just put it on embedded cable 2D. So suppose the other items are true. Then I click on OK. So now I define the necessary parameters for the model, and just now I can save and run the model. But it takes time, so I want to open another model which I already defined before. This is the same model which I defined with just finer mesh because the mesh size here is smaller.
It takes time, but okay, only for people to know. So it takes 10 minutes, but okay, I think
10 minutes, less than 10 minutes.
Because it's material nonlinear analysis up to the collapse of the beam. But yeah. I think your choice is okay.
Yes. When we click at run, it will automatically run pre-FEMIX and FEMIX. And then when we click on generate results, for example, I click on generate results, we will see a window for example, we don't want the output for all combinations. We can just choose the desired combination. Also, we don't want the output for all groups. We can limit the groups which we need. And also, we can choose which types of output we need: displacement, stress, strain, or crack pattern. I dismiss for now. And then we go to result tab. For example, here we need to see the displacement in D3 and the S step, for example, the last step, which we can see that in this counter, we can see the displacement values in the left panel. We have different options, for example, to seeing the deformed shape. I just click on deformed shape. I increase the deformed shape scale to 10 times. You can see it will be more visible, the deformed shape. Also, we can increase the number of colors in these contours. For example,
Caviar, you can indicate that clearly in transition between the blue and CI color, you have the distortion of the elements, typical of a shear failure. If you see,
here.
so
yes,
it's quite nice. It's quite nice. Open. So you have a low angle. So this means that it's clearly a shear failure. Yeah. And when we will see the crack pattern, we will see in fact
that's the shear. Yes, exactly. The title of the paper was that the investigation of the shear failure. We have distortion, and now in crack pattern, as you told, in the crack pattern, we can just check in the web, and I didn't. It's beam. Yes, beam in step 55, and the crack pattern. I will increase the size of the width and length of the crack to be more visible. And now, after refreshing, this is the crack pattern here. Exactly as you told, it's exactly the location of the shear failure. And we have a legend explain each types of failure. This is the crack is opening. And we have in the right menu in the property.
I can take the opportunity to see a very nice thing. So to report. So we have the red color, as is indicated, is in the opening process. So the crack is opening. Yes. But you see in surrounding, no, please maintain the green, because the green is closing. So this means that we have a localization. The crack is opening, and since this zone is opening, the stress is decreasing because it's a softening. And in surrounding zone, we have an unloading stress state, and this is the green crack. So the cracks start closing. So this is quite nice, and this is what happened in reality. Okay, thank you.
Exactly. Okay, and we have different outputs such as stress, strain, and then we can go to the graph. Here we can just choose between I want to draw the load deflection curve. So for x-axis, I have displacement. For y-axis, I have the reaction force. Because the displacement is in the minus the direction, I will multiply it by -1. And also because the multiplier, because the units are in Newton, and I want the force in kilonewton, I just can multiply it by this value. The direction for degree of freedom, let me click on this. The degree of freedom for displacement is Z direction, it's D3, and for force also is F3. We can choose on this interface by clicking on this mouse sign and just click here, and then okay. Now we can see that the point number is 2159, and if I click again, it will be the same point. And for the support, I can do the same process for clicking, selecting the supports. Suppose it's correct. Yes, it's 14 and 104. Okay, and then I click on plot graph. It takes a bit, and now we can see the load deflection curve in kilonewton and in It's because I reverse the multiplier, I reverse the displacement direction, it's in a positive direction. We will have the load deflection, and by clicking on this icon, we will have the output on Excel, and just we can draw the shape on Excel. Okay, this is the introduction of the application, and thank you for your attention. And I hope to be able to release the final version maybe in the next month, in the September, because it needs to be more tested in order to have an application without any error.
Many thanks, Kamiar. So, well, but I suppose we can have a, well, we have a period for questions or for something from the audience, because we have a very good audience. Yes. And it will be nice to have a, well, their comments, suggestions. So as Kamiar indicated, so the application is not totally ready. And so we will have, we need some more weeks up to introduce some fundamental part not yet implemented, but I think the advanced stage is already very good. Well, so please, comments, suggestions from the audience, please. Nobody has suggestions, so. We
have a question in.
We have a, okay, Reza is making congratulations. Okay.
The interface element. I can just, if you want, I can just explain very fast about the interface element.
Yeah, okay.
Let me show the interface element. Just let me share again. But for the interface element, for example, here in this case, we don't have any kind of interface element. I want to add an interface, for example, on the bottom bar. I go to element properties. Let me just save as my model with another name. I go to element properties. I will remove the bar bottom at bottom. I just delete this row. And then I'm going to tools and clean model and remove unused elements and points. And then in the mesh, we had the bar on the bottom. So in this time, I want to keep the duplicate nodes and generate the interface elements, and then generate mesh and add to model. Yes. Now we have the interface element. As you can see in the red bar, we have the interface element. You see, this is the interface element which already generated automatically. So we don't need to do a very complicated task. Then here in this table, in the element properties, this is bar bottom interface element. And now we can just attribute different, we can assign different attribute to that interface element. This is a interface line element. What kind of material is it? So for example, here we have 301, and then we can add a new row, and we have, I already defined an interface element load. So we have the interface element properties, and we can just analyze the model.
Hello, can you hear me?
Reza, are you uploading? Okay, good. Yes, Luis, please.
Hello, good afternoon, everyone. First of all, congratulations, Kamiar. I think it looks amazing. It seems very nice, and it solves a lot of problems for us that usually use FEMIX. So this is a critical situation to be able to quick and easily visualize the results and extract the output. So I just have first one question. That is, this software that you are this application, is it a standalone application, or does it have some dependencies? Do you have to install?
No.
Because from what I understood, you use Gmesh and Paraview, no?
Yes, it depended to other softwares, but you don't need, the user doesn't need to do anything. It will be a single package. You just install it such as other softwares and will use it as I did. You don't need to do any more action for link between the other software, because everything is already internally inside the application.
Okay. So, so what do you mean? It comes in one bundle, right? So the user doesn't have to go to the Gmesh website and download it, and to the Paraview. And okay, okay,
everything included in the application, and the user doesn't need to do anything.
Okay, very nice, very nice. And another thing, and maybe this is kind of a suggestion. I saw that when you were inputting the information about the element properties, you had to go through a lot of fields in the table. So maybe it will be nice. I'm sure you already are thinking about this, but it will be nice to have some kind of pre-filled option, maybe to help. For instance, if you pre-fill all the fields, maybe then the user just have to change the ones that that doesn't interest her.
Yes.
And another thing that I saw that I suppose it will improve in the future, because you made already a lot of progress in this application from the first time I saw this. And when you want to delete some kind of geometry part, I saw that you had to go to the button each time that you want to press to delete.
Yeah.
Right?
Yes. So for cleaning the model from the deleted items.
Okay, is it possible, or maybe a suggestion, if it's possible to implement some kind of keyboard bind, you know, because in this way it would be easy for instance, one to go and press one key on the keyboard and immediately get that delete option. Yes, maybe just a suggestion for the future, maybe, or the fence style of deletion, but I suppose that's a little bit harder to implement. I don't know, but the key bind, I think it would be cool to have. And also maybe I will stop. Just one final question. What if I saw that when you generated the mesh, you had to go like part by part, right, layer by layer, and generate the mesh. The one question is, what if, for instance, if I want to refine the mesh, I would have to go to each part and generate again, right?
Yes, because the mesh was dependent on different parts, but we can draw different parts in one single, different items, different elements in one single part. So the mesh will be generated in one group. But the problem is it will be difficult to control them in FEMIX, because the layers are controlled by the group name, and the group name is dependent on the model in the part name.
Right. So maybe it would be cool in the future also if you want maybe to implement some kind of auto refinement option or maybe something similar. But I think it's well, I don't have any more question. I just thanks for the answers. I think it's very cool. The option to generate the interface elements, the embedded cable elements, is very nice. It solves also a very an issue that we had to face every time.
I had
and that is very cool. Yes. Yeah. Also the interface, it's very good. It's very good. So congratulations and keep up work. Thank you, Kamir.
Thank you, Luis, for your comments and suggestions. They are in fact very nice. Some more questions? Suggestion? Well, if not, many thanks. So we will try to have this type of seminars in the future. So continue to demonstrate what people are doing internally in different subjects, in different research areas, because the main objective, as I indicated in the beginning, is that everybody knows what we are doing, what the colleagues are doing, and eventually, and this is most important, to straight collaboration. This is, in my point of view, a very important aspect. So many thanks to everybody, and well, we will maintain in contact. So thank you and good afternoon.
Thank you.
Bye bye. Bye
Thank
bye.
you, sir. Bye.
Bye bye. Bye bye.